The ability for a conductor such as a wire to store energy in the form of a magnetic field leads to a property known as inductance. A way to understand this is that the magnetic field that is set up due to the current wishes to stay intact and thus opposes any change in current flow. This temporary resultant potential is termed the back electromotive force, or back EMF, and can cause a lot of issues if handled incorrectly. As a visual example, if we were to disconnect an inductor from a current source and immediately connect it to a resistor, the inductor would instantly create a voltage drop opposing the change in current. Therefore, current would flow through the resistor for some time. Broadly, this understanding allows us to link our understanding of magnetism with our understanding of inductors. Self-inductance is when a rate of change in current in a conductor produces an EMF in the same conductor. Mutual inductance is when it produces an EMF in a nearby conductor. In this case, the two conductors are magnetically linked, as is the case in transformers. We'll now take a look at the internal and external inductance of a wire. To formulate an equation for the inductance of a two-wire system, we need to understand the concept of flux linkage. This is an extension of magnetic flux and essentially serves to describe the effectiveness of the flux from multiple sections of a conductor. The most common usage of this property is in describing the different magnetic linkages between turns in a coil, N multiplied by phi. In our usage, however, we'll be analysing the linkage between different sections of a conductor core. We know that the inductance of a material is directly related to its flux linkage divided by its current. Knowing this, we firstly lay out our equations for the B fields from before. We then take the derivative with respect to R, being the radius of the Amperian loop, to find our differential flux. This is the rate of change of flux through a cylindrical surface about the wire. To reach our differential flux linkage, we then apply a ratio to both the internal and external formulae with regards to the relative area enclosed by the two Amperian loops, the internal and external ones. Of course, in the external case, all of the conductor is enclosed within the Amperian loop, so the value remains the same. However, in the internal case, only a portion of the conductor is enclosed, as described by small r squared divided by big R squared. To determine our flux linkage proper, we will need to integrate over a distance d. For a single wire, this should be an infinite integral. In a two-wire system, however, we select d to be the distance to the return path, another wire of opposing current flow. Here we are assuming the radiuses of these wires to be the same. We can now begin to consider the two-wire system in more detail. Integrating the above across their relevant domains, from the core to the radius of the wire for the internal case, and from the radius to the edge of the other wire for the external case, we find the flux linkage for a single wire with the other. We divide by the current, as in our above equation, to find the inductance. We then double these values through the principle of superposition. Following this, we sum the internal and external inductances to find the total inductance between two wires in henries per meter.